Hey guys, my name is Jack Stewart, and this is my Lab 5 for Physics 2212. This lab is on magnetic braking with Faraday's Law. Let's hop right into it. First thing we're going to do is the introduction to the lab. The purpose of this lab, as given to us, was to collect observational data of a magnet falling through a conductive tube of aluminum foil. We're going to use GlowScript and code given to us to model the magnet-tube interaction computationally, and we're going to compare our predictions with the observed data. Some of the topics we'll be covering in this lab are Faraday's Law, Ohm's Law, Lenz's Law, magnetic field, and magnetic flux. Here are some of the formulas we're going to be using. On top is the Biot-Savart law, and on bottom is broken down, or the base formula for Faraday's Law, which just EMF is delta phi over delta T. So the setup for the lab is pretty simple. There's only really two steps. We got a roll of aluminum foil, which had to be of a certain thickness. I found one at home, and we were going to drop the magnet we were given through the roll, and we time it and repeat it 5 times to get the average time to avoid discrepancies or outliers. And I actually did it 6 times because I messed up one of the times. So here's the data we got. The length of our tube was about 1/3 of a meter, 0.32. The inner radius of the tube was 0.02 meters, and the outer radius of the tube was 0.028 meters, which puts the thickness of our aluminum foil at 0.008 meters, which is greater than we needed to have. The mass of the magnet was 0.024 kilograms, and the average time I got from my readings was 1.64 seconds. The next thing we're going to hop into is the GlowScript code, and we were given a template for this on Canvas, and so I use this, and as you can see, this first step was creating the tube. Basically, I plugged in the length, the width, the inner radius, and the outer radius, which is just the width plus the inner radius, and then the middle section was given to us, and the bottom section is what actually creates the tube. And it's created using different segments, because what the circuit of the tube really is sections of rings. So then the second part is creating the bar magnet. As you can see, I plugged in the mass, and then we visualized the bar magnet with basic code. And then the second part is actually code we used from my Lab 3 video that we recycled. Here was the output of the code I got. As you can see on the left side, the tube is created, and then it puts out the time in tube, which is computationally 1.747 seconds. And so on the right, our experiment, when we actually did it, got us 1.64 seconds. So we were off by just over 1/10 of a second. Finally, we're going to wrap up by answering the reflection questions. The first one is, what if the resistivity of the conductor were reduced as close as possible to 0? How would the dynamics of the falling magnet change? And basically, the magnet would not fall through the tube. The braking force and gravitational force on the magnet would cancel each other out. And so the magnet, theoretically, would just sit and stand still. If it were really close to 0 but not 0, it would eventually maybe fall through. Because as we talked in the beginning of the lab, the magnetic force is just going to be the force of gravity, 9.81 meters per second squared, times the mass of the magnet. And then finally, the second question we're asked is, what if holes or slots were cut in the tube? How would this affect the ring currents in your model? So basically, the magnet would fall through the tube much quicker, as the current flow through the tube would not be seamless. As we talked earlier, the tube is created up of ring segments. And so having holes, the rings are not connected, or even slots, the rings aren't fully connected, so the current doesn't run fully around, and the force stopping the magnet from falling the braking force would not be as strong. Thank you guys so much.